In this video, I'm going to talk about simple linear regression, a means of establishing a relationship between a numerical explanatory variable and a numerical response variable. We are going to do some exploratory data analysis, the frequentist model fitting, the Bayesian model fitting, and I have to say that all codes, data and codes to run this analysis are in the following website, in the book website. So simple linear regression, the goal is to obtain the best fitting line that relates a numerical response variable with a numerical explanatory variable. The best fitting line to a cloud of points. So a linear regression is a special case of the general lineal model. The general lineal model was the main method, the workhorse of data analysis during most of the 20th century. So its basic assumptions are that the response variable follows a normal distribution with a given mean and variance, and that the mean has a linear relationship with explanatory variables. They may be numerical, as in this case, one numerical, several numerical, one categorical, or several categorical variables. We will see the latter cases in coming videos. And it also assumes that the variance is constant for all values of the explanatory variables. That is, the variance of the response variables showing the scatter around the mean is constant for all values of the explanatory variables. So therefore, the statistical model, the response variable follows a normal distribution with its mean having a linear relationship as shown in the equation, governed by the slope beta 1 and the intercept beta 0. So we are actually fitting for 3 sets of points is the best fitting line that goes through the mean of the mean values of the response variable having a normal distribution. So the mean of the response variable changes in a continuous manner with the value of the explanatory variable being small for this one, medium for that one, and large value for this other. You see that in all cases the scatter around the mean is assumed to be the same for all values of the explanatory variables. So explanatory data analysis, we are going to make a case study in which we are trying to evaluate if the amount of cadmium, which is a contaminant, in the shoot of a grass is related to that in the soil. So the cadmium in the shoot is a response variable, the cadmium in the soil is the explanatory variable. So we import the data, and the data looks, and the summary statistics look as follows. So this is the cadmium in the shoot, the response variable ranges between 16 and 217 ppms, and the cadmium in the soils ranges from 60 to 300 ppms with an average of 180. So the next question that we need to ask in any explanatory data analysis is whether these two variables, these two numerical variables, are related, whether the response variable in the vertical axis is related to the explanatory variables in the horizontal axis. And the answer is yes, as the explanatory variable increases, so does the response variable. And so, although this general linear model assumes that the response variable follows a normal distribution, we must always assess it in order to be able to write the likelihood part of this model, and in order to write the likelihood part of the Bayesian fitting model. So the best way to do it involves comparing candidate probability distributions using the cumulative distribution function and the QQ plots obtained with the package fit distribution plus. So what we do is that we first estimate the parameters of these two candidate probability distributions that we are going to compare to model the response variable. So we are going to consider the normal probability distribution. So we fit the normal the parameters of the normal, the mean and the standard deviation for the normal distribution, and we are going to consider the log normal probability distribution, so we fit the two parameters as well. with these fitted values of the two parameters, we obtain the cumulative distribution function at the left and the QQ plot at the right. So the idea here is to visually assess which of the two distributions is closest to the data. We see here that the normal distribution appears to be closer to the data than the log normal distribution. The actual data are these stepwise values, and this, for instance, this says that almost 75% of the values are smaller than 150 ppms. So here in the QQ plots, we are simply comparing two distributions. An empirical distribution, the empirical quantiles, and the theoretical quantiles. The theoretical quantiles are generated as if the value were to have, the responsive variable were to have a normal distribution, and if the responsive variable were to have a log normal distribution. So the logic between these QQ plots is that these two distributions, the empirical and the theoretical, should be identical if the distributions are the same. So in this case, we are trying to see which of the two lines, the black or the gray, are closest to the line of perfect fit, the 45-degree slope, which is indicated by the straight line. So in this case, we see that the two distributions are the normal distribution for both plots is the best candidate that we have of the two distributions we compare to model the likelihood of the response variable. Then for the frequentist model, we simply use the command LM, linear model, the response variable separated by this symbol with the explanatory variable, and the data are in a given data frame. We obtain a list, it's a type of object, R object called M1, whose summary is the following. So the statistical model written before is that the response variable follows a normal distribution whose mean has a linear relationship with the numerical explanatory variable governed by the intercept and the slope, and there is a variance of the response variable. So this model can be rewritten in the following way, as the straight line that we all know, and residuals, which show the scatter around the mean. The mean is reflected, of course, by these two terms. So here is the slope of minus 19.03 with the standard error of 8.35. The standard error is the precision with which the sampling intercept estimates the population intercept that we would obtain if we had an exhaustive sample of the statistical population. This t-value corresponds to the ratio between the intercept, the estimated intercept, and its standard error, and this p-value simply detects whether this estimated intercept with a given standard error is significantly different from zero, and we actually don't care about it because the parameter that shows the relationship between the explanatory variable x and the response variable y is the slope, whose value is 0.75 with a standard error of 0.4, and the t ratio is equals to 18, and this is the p-value, and because the p-value is a lot smaller than the conventional threshold of 0.05, we say that there is a statistically significant, that this slope is significantly different from zero, and therefore that there is a relationship between the explanatory linear relationship between the explanatory variable and the response variable. Then for the residuals we have 20 data points, then we have 20 residuals. The residuals that are going to be shown in the next slide these are the descriptive statistics of the residuals, which are of little to no use. So for any value of x, we can use this equation to obtain the predicted mean of the response variable y. We also have the residual standard error is the standard deviation, not the variance, the standard deviation, that can be raised to the square, can be squared to obtain the estimate of the variance. And we can obtain confidence intervals for these two parameters governing the relationship between. In every case of the general lineal model, we can partition the total variation of the response variable y into the explained and the residual or unexplained parts. So here at the left in this equation, we have the sum of the square difference between each data point and the mean, that is the total variation. And in this equation, we add and subtract the same term, that is the predicted value of the response variable predicted by the linear regression we are fitting. Since we are adding and subtracting the same term, nothing changes in the equation. After rearranging terms and developing the terms here inside between parentheses, we arrive at the following. So here we have the total variation at the left. Here we have the residual part, that is the difference between the observed value of the response variable and the predicted value. And the explained part corresponds to the difference between the predicted and the mean value of the response variable. This can be shown in the following diagram. So we have for two data points, here in dashed line is the mean of the response variable. Here is the best fitting line, okay, and this best fitting line, the total variation is partitioned between the blue part, the residual part, and the difference between the predicted values and the mean, that is the explained variation. Dividing the last equation, this one, by the total variation divided by the left-hand side, we obtain the following. Of course, dividing this by the total variation gives 1 at the left of the equation. And here, whereas here we have simply this proportion. This proportion is called here r squared. I'm saying it's proportion because the sum equals to 1. This r squared is the proportion of the total variation of the response variable explained by the fitted model. It's a measure of the goodness of fit of our model. So this is what it is. So we can also obtain, as we from the summary shown in the previous slide, that the adjusted r squared is 94%, which means that our model explains 94% of the variation of the response variable. This partition of variation is the basis of the analysis of variance that I will explain in the video 7 of this series, so stay tuned. So assessing the goodness of fit of the model to the data, so the statistical model that we wrote in this way can be re-expressed in the following manner, with the residuals now having a normal distribution, expected to have a normal distribution with a mean of 0, because the mean is absorbed by this relation fitted, and a variance sigma squared. A perfectly fitted model would then have residuals with a mean of 0 and a variance of sigma squared. Residuals will have a random appearance with an approximately mean of 0, as I said again, and without any relationship or obvious patterns when plotted against predicted value or against explanatory variables. Residuals should have a normal distribution because of what I just mentioned, and they have a low sensitivity to parameter estimates of each datum. This is to be evaluated in the case of these models by the Cook distance. The Cook distance is the difference in the parameter values between the entire data set and the data set without the I data point. And this gives you a sort of sensitivity analysis of how sensitive are the parameter estimates to the values of each data point. So residual analysis is carried out by the qualitative interpretation of a series of plots that we are going to start here to see in the coming slide. And this series of plots, of course, may vary slightly between models depending on the number and types of explanatory variables, but the idea is the same. What I want to say is that residual analysis requires a sort of progressive learning that you would acquire through the visualization of the different videos and hopefully the reading of mine and many other books. So the package Broom allows to gather the input for the residual analysis into a single table or data frame. This is very handy. The command augment of this package gathers the response variables, the explanatory variables, the fitted values, the residuals, standardized residuals, which are the ones that we are going to use, and the Cook distances. These are other features which are unimportant to what we are going to do here. So with this input that we gather with the command augment, we form a data frame, and with this data frame we generate the following plots. So here we have the plot of the standardized residuals against the fitted values, and we see that roughly the variation, if you divide by I this in two halves, the left-hand side and the right-hand side, roughly the scatter of the points is similar in the left-hand side compared to the right-hand side. The amount of variation above the range of variation for the positive side of the residuals is similar to the negative, not identical to the negative side of the residuals. So we don't see any we don't see any relationship between the points in this plane. When plotted against, when the standardized residuals are plotted against the explanatory variables, we see more or less the same thing. That is, we don't see any obvious trend suggesting that the model is incomplete and need to be amended. The QQ plot gives us an assessment of whether these standardized residuals are follow a normal distribution, as they should when a model fits perfectly the data. And we see that the points are all very close to the best fitted to the line of perfect fit, and all inside the envelope, this gray envelope of 95% confidence. So all this shows a great fit of the model to the data. And finally, the Cook distance, we only see one point that might have potential large influence on the parameter values. So with experience, so what we could do, we could refit the data without this point and see if there are any important qualitative changes in the parameter values. The idea is not ever to discard information. Empirical information is somewhat sacred. We don't throw away empirical information unless we have a very clear idea of that a given data point or given data points are wrong. So my suggestion is to assess the sensitivity of the model parameters to eliminating eventually one of the data points, and always to show the two fits, one with the entire data set and another with some apparently extreme data points. So at this point, the model seems to have a very good fit to the data. Communicating the model results with another command of the Broom, of the package Broom, the command tidy, we can obtain a table with which is a data frame, type of data frame, with the parameter estimates, standard error, essentially all the same information that we obtained in the summary, besides the lower and upper limits of the 95 confidence intervals of the parameters. This could be used to make a plot, but I mean it's pointless to make a plot with so little information. We can also produce the conditional curve with the package ggeffects, which the main command is ggpredict of this fitted model. Here we include the name of the explanatory variable, and here we obtain the values of the explanatory values, the predicted values, and the confidence intervals with which we can make the following plot, showing that the best fit line actually is very close to the points, which is of course congruent with the height r squared that we mentioned before. In the case of the Bayesian model fitting, the flow of interaction between you and the software will be in all these video fitting Bayesian models will be the following. First, you or I would interact with RStudio, that in turn sends all the instructions to R for processing. Specifically within R, we are going to use the package VRMS as a front end that will generate a C++ file that will be sent to Stan, compile and send to Stan. Stan will use the Hamiltonian Monte Carlo method to estimate parameter values. Its results, the posterior distribution, will be sent to VRMS and which is part of R, and will be sent back to RStudio for you or I to see it. So it is a lot simpler than it looks in this complex diagram. So let's recall the statistical model now that we have mentioned already several times, with the response variable having a normal distribution with a mean that is linearly related with the variable explanatory variable x and variance. So the fundamental equation of Bayesian parameter estimation is now repeated here again in the screen. That becomes, in this specific case, this is the posterior distribution, the joint posterior distribution of the intercept, slope and variance given the data, and that is this is the likelihood part, is the probability of seeing the data given the values of the given sets of values of the parameter sets of values of the parameters. I recall that the intercept and the slope together with specific values of the explanatory variable x gives the mean of the normal distribution, and this is the joint prior of the three parameters that are in the model. So this model has three parameters, so it's indispensable to be able to write the model so that we know for which parameters we need to specify prior distributions. So the package VRMS has a very useful command for this. So the command is called getPrior, in which we put the formula, response variable separated by this symbol with the explanatory variable, the data frame, and we specify that the family is Gaussian. It could be any other probability distribution. This is of course Gaussian because this is part of the general linear model. So now we see the default priors. So this is the slope for the variable, for the explanatory variable soil. This is the intercept, and this is sigma. So what we have here is a very complex and uninteresting way of specifying that these are weakly informative priors. That is, priors that have by default. So the package VRMS by default has weakly informative priors, meaning that we have very little information about the potential values of each of these three parameters. So we can now arbitrarily define, at this point, priors with the function setPrior. With the function setPrior, we create the object prior.m1. So we set the prior normal with a mean of 0 and a standard deviation of 20 for the intercept. We set a prior of normal with a mean of 0 and a standard deviation of 2 for the slope. And we use the Cauchy distribution, which is a sort of Gaussian-looking distribution with thicker tails. For the class sigma. Class sigma is the standard deviation. So what we are saying, so it's a lot easier to explain what the implications of these priors if we plot them, which is what we are going to do now. So in the intercept, we see a standard deviation, a normal distribution centered at 0 with mean. So it means that 95% of the values expected for the intercept range between roughly 36, minus 36 to plus 36. This is a very wide range. For the slope, we are saying that roughly we expect values between -4 and +4 for the slope. Could be anything between -4 and +4. This is the kind of knowledge that we have about the slope governing the relationship between the explanatory variables and the response variable before seeing the data. And we now we see for the sigma, the standard deviation of the response variable, we are plotting half of the Cauchy distribution. The Cauchy distribution would go to the negative part, but the program, this package BRMS is smart enough to know that we are just using a half Cauchy. This plot is implying that we are expecting smallish values of the standard deviation to be far more likely than high values of the standard deviation. Okay? So our first Bayesian model, we used the command DRM. This is the formula written in the same way as we did for the frequentist model. This is where the data is in this data frame. Family Gaussian, that means this is a case of the general lineal model. And for the prior, we use the object prior dot and 1, the one that we set up in the previous step. We use a warm-up of 1,000 iterations, meaning that the first 1,000 parameter values would be generated and thrown away to be independent of the initial random values of the 3 chains, once per parameter, of the chains of each parameter. Future equal true is a way of indicating that we want to parallelize the calculations, which means that part of the calculating effort will be sent to the different processors that you have in your machine. This is sort of irrelevant for this very small data set, but for complex models it may have some interest. Here we are saying that we are going to use 3 chains. That is where you are going to use, if you wish, 3 independent explorers of the parameter space. In the example that we show in the previous video, we use just 1 chain, and we are going to retain the last 2,000 iterations of these chains. So we have for 3 chains of 2,000 parameter estimates after discarding the first 1,000 values. So the summary of this model is the following. So we have a general information here in the top, basically reiterating what we put up. Then we have the parameter, the population level estimate, that is the effects of the parameter. These are the parameters affecting the mean, and this is sigma, the standard deviation. So let's put some order to understand what this is. So first of all, we have the descriptive statistics of the posterior distribution for each of the 3 parameters. We have the mean, we have the standard deviation, which becomes the standard error, and the 95% credible intervals for each of the 3 parameters. And then we have metrics of the convergence of the chain. This is what I need to explain separately. So we need to interpret first whether the 3 chains converge to the same or rather similar posterior distribution. Then we merge the 3 chains and we have the complete analysis of the results. So let's analyze first the metrics of convergence of these parameters. So let's look first at the posterior distributions. Here are the posterior distributions of the 3 parameters. You see these are wiggly lines. These are not theoretical lines produced by some mathematical function. These were obtained by the estimation, by the joining of the 3 chains that we used. Okay. The 95% credible intervals, it means that the slope, the probability that the slope be higher than 0.68 and smaller than 0.84 is 95%. This is the probability that the slope is bigger than a given value and smaller than another value. And the convergence of the chains. Now let's look at first this R hat. This R hat is an indication, is a ratio, without entering into the details of the formula, is a measurement of the variability between and within chains. So if the R hat value is closer to 1, this means that the chains have converged to the same common stationary distribution. We will see what that is in a second. And the ESS is the specific sample size, effective sample size, and this is roughly an indication of how many sample estimates retained in the chains we have that are statistically independent. And roughly, this is okay if we have several hundreds, or if you are picky, more than 1,000. So let's analyze first visually the convergence of the chains. So we have the three chains for each of the parameters of the model parameters. We see that roughly the same, the means and the shapes of the three distributions are identical, which means that they have converged roughly to the same mean and the same scatter or standard deviation for each of the three parameters. This is a great indication of the convergence of the chain to the same stationary posterior distribution. So we also need to examine what they call in the Bayesian jargon the degree of mixing of the chains. This is evaluated through the trace plots. So what we want to see here, we have them superimposed, the values, the colors corresponding to the three chains. What we want to see here is that the chains have, all of them separately, explore more or less similar ranges of the values. What we don't want to see is that one of the chain got stuck in extreme values. For instance, the dark blue chain got stuck for a large number of iterations in large values of a given parameter, and got stuck and didn't explore reasonably well the span of values explored by the other chains that were here considered. So we also assess the independence, statistical independence of the sample parameter estimates, those retained in the chains, and we do that by the autocorrelation coefficient. And this essentially measures the correlation of values separated by 1, 2, 3, 4, 5, up to 20 steps in the chain. This is done because you might remember that the Monte Carlo, the MCNC type of algorithms is based on a Markov chain, and in the Markov chain, consecutive values are related. So what we want to see is the degree of statistical independence of values separated by given numbers of step size. So these are by and large very weakly correlated. The highest value is 0.2 or 0.1, actually 0.15 more or less for one of the parameters. So this is, it says that the three chains, the conclusion is that the three chains have converged to the same posterior stationary distribution. It means that we can merge them. Each of the chains have 1,000 values, that they are well mixed, and that we have many statistically independent parameter estimates in the chains. So we are now going to assess the goodness of fit of the model to the data. And so just as we obtain a posterior probability distribution of the parameters, we also obtain probability distributions of the residuals for each data point. Unlike frequentist statistics, in which we obtain a single residual for each data point, now we obtain a probability distribution of the residuals for the data points. So let's do it. Let's use the command residuals of our fitted Bayesian model. The type of the residual is type Pearson. We obtain 1,000 draws and no summary. So this object res has the dimension of 1,000 rows, because we ask for 1,000 draws from the posterior distribution, and 20 columns, one for each of the data points. So the Pearson residuals is more or less a type of scale residual that is often used to assess the degree, the goodness of fit of the data. So for each data, if the 20 data points, we have 1,000 residuals. So we are going to summarize these residuals for each data point with a summary in order to make the plots. And the way of doing it is, instead of asking for summary false, we ask now for summary true, and that will compute the mean, standard deviation, and credible intervals of the residuals for each data point. And for the same reasons that I alluded above, we also obtain a posterior distribution for the predicted values of each data point that we again need to summarize in the same manner as we did before. We can also obtain what they call the Bayesian R-square, which is related to the variance of the fitted values. These are the fitted values and the variance of the residuals. This very simple ratio amounts to the R-square, which we now have not only the point estimate, but also the error and credible intervals of the R-square. So again, in Bayesian statistics, you not only obtain the estimate as a mean of the posterior distribution, but then an entire posterior distribution that can be summarized in different ways. This metric of goodness of fit of Bayesian models applicable to any Bayesian model stems from the paper by Gelman et al. 2018. So we can use now the package Broom that was very handy to gather in a data frame the input of data analysis. We must do it by hand, but we by now know enough about R syntaxes to do that. And with that, we construct the same three plots, the analogous three plots that we obtain for frequentist residual analysis. And we see more or less the same result. We see a random scatter of points here when plotting the residuals against the fitted value, a random scatter of points here when plotted against the explanatory variables, and we see that the mean of the residuals roughly have a normal distribution, suggesting that the model had a very good fit to the data. In order to communicate the results, we can obtain the condition. We use the command conditional effects that is part of BR of the package BRNS in order to obtain the curve. And the curve is simply the following. So we see a fantastic curve that goes very well through the data, which is of course consistent with the high values of the R-squares. We can also plot the means and the 95% credible intervals of the estimated parameters, which is simply this, and this is very handy. The light blue lines correspond to the 95% credible intervals, and the dark blue lines correspond to the 50% credible intervals, which we now obtain. For the slope, simply there are of course credible intervals. It's just that we don't see them because their magnitude is very small compared to the magnitudes of the other parameters here plotted. So in this video, we explain simple linear regression. We did the exploratory data analysis, the frequentist fitting, the Bayesian model fitting, and I recall that all the codes to run this analysis can be found in the book website. I thank you for your attention. I hope that you found this video interesting.